Hello friends, in this video I'd like to solve the following problem from the Serbia and Montenegro International Mathematical Olympiad Team Selection Test 2005, problem number 1. We wish to show that cosine of pi times r is never equal to 3 over 5 for any rational number r. It's a nice problem from trigonometry. There are many ways to solve it. Here is my suggestion. I will prove it by using famous Chebyshev polynomials. Recall that we have the following sequence of polynomials: t0 of x, which is constantly 1, t1 of x, which is equal to x, its identity, and nth polynomial is 2 times x times n minus first polynomial minus n minus second polynomial for every n greater than or equal to. These polynomials, t0, t1, t2, t3, and so on, they are called Chebyshev polynomials, and they satisfy the crucial property that for every natural number n and every angle theta, cosine of n times theta equals nth Chebyshev polynomial at cosine of theta. And for our problem, suppose to the contrary that cosine of m times pi over n is equal to 3 over 5 for some integers m and n, and then use p-adic valuations. Show that p-adic valuation at p equals 5 of nth Chebyshev polynomial evaluated at 3 over 5 is always minus n for every natural number n. Prove this by induction. If we don't know what p-adic valuation is, basically, if we have some rational number, every rational number can be written uniquely as a product of some powers of primes plus or minus. And what is p-adic valuation? Well, there are just these exponents which are right here. So if I call this number u, for example, p1 valuation of u is alpha 1, and so on. pr valuation of u is alpha r. They are just these exponents. These exponents, because we are dealing with rational numbers, they are integers. They may be negative. Okay, so give this problem a try and I will see you in just a minute. Okay, so I hope that you've managed to solve it. I will leave these two facts, the definition of Chebyshev polynomials, and I will use this theorem which I have written. So it's a fact, and we will use it. I will not prove it. It can be done by induction. Okay, and now, suppose to the contrary, that cosine of m pi over n equals 3 over 5 for some integer m and positive integer n. Let's suppose it. It will lead to contradiction, which I will show. So now, if I have this equality, what I can do, I can apply nth Chebyshev polynomial on both sides. And after application, by using this fact, cosine Tn of cosine m pi over n, it's just cosine of m times pi, and that should be equal to nth Chebyshev polynomial evaluated at 3 over 5. What is cosine of m pi? It's plus or minus 1. Actually, it's minus 1 to the power of m. So we have the following. And also, let's define sequence an to be nth Chebyshev polynomial evaluated at 3/5 for natural numbers n. We have a nice recursion for our numbers. 0th number is 1, first number is 3/2, and nth number, it's 2 times x, so it's 6/5, and an minus 1 minus an minus 2 for n greater than or equal to. How do I know that? Well, by the recursion of Chebyshev polynomials. So if I plug in 3/2, here I have 3/2. Here I have 3/2. Here I have 3/5, sorry. Here I have 6/5, and so on. So I am just using my recursion. And now my claim, which I will prove and will be done. I claim that for every natural number n, the p-adic valuation, with p equals 5 of an is always minus n. It's always minus n. Proof. By induction. Well, let's start with n equals 1. P-adic valuation of a with n equals 0, sorry. Of a0, p-adic valuation of 1. Well, 1 is 5 to the power of 0, so this is 0. P-adic valuation of a1, it's p-adic valuation of 3/5, and if you take a look, 5 appears with exponent of minus 1, so it's minus 1. And now, suppose now that in fact p-adic valuation of an minus 1 is minus n minus 1, and p-adic valuation of an minus 2 is minus n minus 2 for some n greater than or equal to. What does it mean? Well, since our numbers are obviously rational, p-adic valuations are only valid for rational numbers. Notice that means that p-adic valuation of an minus 1 can be written in the following way. It's alpha over beta to the power 5 n minus 1, and an minus 2 can be written as gamma over delta 5 to the power n minus 2, where alpha, beta, gamma, delta are some integers not divisible by 5. Very well. Now, let's take a look at an. An, by our very recursion, it's 6/5, an minus 1 minus an minus 2. I'm not mistaken. I am not. Okay. Now, 6/5, it's 6/5. And now we have alpha, beta 5 to the power n minus 1 plus, minus rather, gamma delta times 5 to the power n minus 2. And now, what can we done? Well, in the numerator we have 6 alpha over beta 5 to the power of n minus gamma delta. And now let's do one trick. Let's write 25 gamma over delta 5 to the power of n. And now let's introduce a common denominator. The common denominator is beta delta 5 to the power of n. And in the numerator we have 6. Maybe I will write following way: beta times delta. Here we have 6 alpha delta minus 25 beta gamma. And now let's notice a few things. First of all, our numerator is not 0. Because, why is that? Well, notice that 5 divides 25 beta gamma, obviously. And obviously, 5 does not divide 6 alpha delta. How do I know that? By assumption. It was my assumption. And that means two things. First of all, an is not 0, and moreover, 5 does not divide the whole numerator. Likewise, 5 does not divide beta times delta, which means that our p-adic valuation is minus n. So, p-adic valuation of an equals minus n, which closes our inductive proof. Our inductive proof of our claim. But we are just one step before the final conclusion of our video, because now, since I know that my p-adic exponent is minus n, and let's go back to this line. Let's copy this very equation, because now we will have a problem. Sorry. Now we will have a problem. Maybe let's put everything a bit higher. Or not. Now we have a problem, because what's the p-adic valuation of minus 1 to the power of m? Well, this p-adic valuation, it's 0, because 5 appears with exponent of 0. And here, p-adic valuation of Tn 3 over 5, we have established is minus n. So 0 equals minus n for positive integer n. Contradiction. We have a contradiction. Which means that in fact, our initial supposition that there is such a rational number r, that cosine of r pi equals 3 over 5, it was just wrong. So it means that there is no such rational r. And that closes our proof. It's a very nice problem, I'd say. Thank you very much for watching, and I will see you next time. Goodbye.